One of the nicest constructions in real analysis is the notion of lim supremum of, say, a sequence. The first beautiful thing about this is that it is always defined, no matter your sequence is convergent, oscillating, going to infinity, negative infinity. It's always a defined quantity, and we love that kind of things in analysis. But usually the definition of limsup is very tricky in textbooks. There is some picture which is illustrating and nice, but then the very definition itself gets kind of convoluted. There is a lemma behind it and so on and so forth. And the worst thing to me is that the definition itself seldom gets used in any proof involving limsups. And here I'm proposing kind of a revolutionary way, maybe a controversial way of approaching limsup in undergraduate texts, so that maybe it will be more intuitive to students and easier for them to work with. Here, for example, is the definition of limit supremum from the Wikipedia. One definition that is used here is you define the supremum of the tail of the series, and then that becomes a decreasing sequence of n, the cutoff, and so it has a limit. But this limit could also include positive infinity and also negative infinity, some annoying cases maybe. And the other way of doing it is through limits of all possible convergent subsequences. So you look at the set of E, for which there is some subsequence converging to those values, and then you take supremum of them. But often these definitions are not what is actually used in proving facts about lim supremums. What I propose is to begin with the most useful and critical property of lim sup, and why not just make it a definition to begin with? Precisely, let's say we have a sequence of real numbers. I want to define what it means for lim sup to be less than a number. So for a given number, a true number, not including infinities, we say, I'm defining something. I'm not even thinking of this lim sup. I'm not saying this is a number or whatever. It's a symbol, just at the symbolic level, less than alpha if all but finitely many xn satisfy xn strictly less than alpha. I don't say if this is a number, an operator, a function, nothing. I simply write this specific string of letters to mean exactly what it says here, which is equivalently saying that after a cutoff, all xn will be strictly less than alpha. So now I have a notion of what this means. If I really insist on defining lim sup as an xn, I can go with a second definition, and I say that lim sup of xn is plus infinity if no alpha as above exists. Okay? And I write that lim sup of xn is equal to some beta, let's say for this time plus infinity, if beta is the least value of numbers that satisfy the claim above, namely if alpha is such that beta is less than alpha, then all but finitely many and so on. And in this case, beta equal minus infinity is a possibility because the least of such alpha could be negative infinity. We could always find a smaller and smaller alpha satisfying this property. Now here's a subtle question. Why can we not combine the two definitions? The answer is that this property is not stable in the sense that it is true for every alpha strictly bigger than lim sup, but it is not true for equal lim sup itself. will fail for choosing alpha to be equal to limsup. And that is the case, for example, if you have a decreasing sequence converging to limsup, which is just a limit. And we see that this property actually, you never are strictly less than that. But as soon as you take some alpha bigger, the tail goes under it. So there's that instability in this. It's true for every number strictly bigger than limsup, but not limsup itself. So that is why we cannot really combine them into one definition. In other words, the property that defines limsup, basically, does not hold for the limsup exact value itself. Now I'm going to illustrate how using the definition that I mentioned can simplify some proofs and avoid like case-by-case analysis. So here it was a very old question, very common homework question. You probably have solved it at some point in your life. You define a new sequence from an old sequence by just averaging the first and many. And the question is that prove that limsup of this averaging cannot be bigger than the limsup of the original one. Of course, you know why it should be true and then how to approach it. Now, there are many solutions to this, and people have written several of them. Let me show first them. Very natural. You imagine that limsup is sigma, and then maybe limsup of the original one is a, and you want to show that this is less than. And then you go through breaking at the right threshold, and the calculations work through. A second proof using similar idea, working with epsilon. So your property of limsup is that if you add an epsilon, something happens. If you subtract, there's always something bigger, and so on. And again, you just do the calculation. The core calculation is this breaking into the right cutoff, and you get it. And if you consider these solutions and many others, you see that they have ignored the possibilities that the limsup could equal plus infinity or minus infinity, because the moment people say, suppose sigma is the limsup, they're subconsciously imagining that it is a finite quantity. But now, here's a solution that I wrote to this, just to showcase how using inequality is much better than using an equality. So I write that an answer that treats all cases, including plus minus infinity, at once. And so the proof starts by saying that if the bigger quantity that you want to prove is bigger, if it's plus infinity, nothing to prove. And so if it's not plus infinity, that means there is some real number that satisfies this property that I emphasized, that limsup is less than that. And the meaning of that, in our definition, is just the very definition. If someone uses a different limsup, the property anyway is that after some threshold, all the values go strictly under L. And here is the point. If L is set equal to Sn, this won't be true. Then you have to add an epsilon and so on. But this is much cleaner. You already assume strictly less than and then that. And then the same covering here and there. And then I end up proving that limsup of the averages is also less than or equal to L. And then look what I have proven. For every real number L, if limsup of Sn is strictly less than L, then the limsup of the sigma n is less than or equal to L. And but what is limsup of Sn is smallest of all such L. And that immediately gives you the inequality you want, including the case of minus infinity. It's a much shorter proof. I haven't cut out any details here, but it treats all the cases. And I think the catch here is that I use an inequality to begin with rather than an equality. I hope this motivates you to introduce limsups to your future students as a property rather than just as a number. Don't rush with getting to a number first. Let me know what your comments are, if there is a way of making this even much more textbook quality. Will this suggestion of mine, defining limsup less than alpha as property in its own, will ever be embraced by any publisher, say, to be included in a textbook. Have a nice day.